Okay, good day. So today we'll be discussing another topic in mechanics and hydromechanics, which is viscosity. So what is viscosity? So simply viscosity is the resistance to flow or to deform is known as viscosity. So fluids resistance to flow, that's simply viscosity. So the higher the resistance to flow, the more viscous or mas malapot yung fluid. While the lesser the resistance, so mas madali mag-flow, mas lower yung resistance, mas madali mag-flow, and the viscosity is lower. Okay? Okay, so what are the systems on board where the viscosity of a liquid is applied? First, we have for engine lubrication. So, why is the viscosity important in our engine lubrication? So, if your engine will have a lubrication that is low in viscosity or mas malabnaw, so if it's as low viscosity, then the protection from friction, from noise, and from metal to metal contact lessens or goes down. So the more damage it will get, the more damage for the engine parts, moving parts of the engine. While if the engine lubrication is very high or high resistance, so the lubrication will not flow into the engine at the right time. Then when you start the engine, so there will be damage also. So prevent because proper temperature and proper viscosity of engine lubrication reduces friction, noise, vibration, preventing wear and tear of the engine parts. Okay. Next, we have propeller shaft bearings. So for the shaft propeller, for our propeller, the shaft that connect the thing that connects the engine to the propeller is the propeller shaft. And if your shaft is very long, so you really need a shaft bearing that will hold the shaft so that it will not sag or it will not be damaged. So due to its weight, so it will not sag and be damaged when it's rotating. So to prevent sagging of the propeller shaft, so you have shaft bearings that will hold them while keeping it upright, keeping it parallel with the engine and the propeller. And when it's rotating, so the bearings will also hold the shaft while it's moving or rotating. So since shaft bearings need lubrication, then it is very important to have the right viscosity for the lubrication of our shaft bearings. Okay, wait a minute. Okay. So we have also thrust block. So from the engine, from the propeller, when the propeller moves or rotates, so there will be a forward force that will be produced from the propeller into the engine. So to protect that forward force or that thrust force, so there must be a thrust block that must be installed between the engine and the propeller to prevent thrust force from damaging the engine or the crankshaft. And since the thrust block is also like a bearing also, so there is a lubrication for it to operate properly. So the forward thrust is transmitted to the hull of the ship. Okay. Oops. Okay, next we have some engines with high speed that is used for propulsion or for any other sources, for shaft generator maybe. So there is a kind of reduction or increasing of speed depending of the use. So if you have a high-speed engine connected to your propeller, then you need to reduce the speed of the engine using a gearbox. So the rotation of the engine will be reduced using a gearbox, and then that speed will be transmitted to the propeller, because a high-speed propeller is not efficient in moving a ship. So it has more losses, energy loss, rather than positive energy used. So you need gearbox. While if ever you have an engine and then main engine, and then you want to connect a shaft generator, so maybe you have to use a gearbox, and then depending on the speed, so you can increase the speed using a gearbox. So since the gearbox is a metal to metal, has metal to metal components inside, so engine or gearbox lubrication is very important for this kind of equipment on board ship. Okay, next we have also the stern tube. So the stern tube is the one that protects, since at the back of the ship there will be our propeller shaft connected to the propeller, and if you don't have any sealing protection, so the seawater from outside of the ship will enter the ship via the propeller shaft. So to protect the seawater from entering the ship, then you should put a stern tube seal at the back of the ship to the propeller shaft to prevent seawater. Okay, so the stern tube is the one that protects seawater from entering the ship. So the stern tube has gravity tanks. So if you want to prevent seawater from entering the ship, then you just have to choose which gravity tank you will use, the higher or the lower gravity tank, depending on the seawater level outside the ship. So that gravity tank will counter or will prevent seawater from entering, because your gravity tank has higher location than the seawater or seawater line outside the ship. So the higher the gravity tank, so the higher the what do you call that, the gravity, or the higher the pressure of your sealing seal oil. So that seal oil will be the one counteracting with the pressure of the seawater level outside of the ship. Okay, next. Controllable pitch propeller. So if you want your some ships have controllable pitch propeller, in which the pitch of the blades moves, so you can use 0 degrees, or depending on what you want to use, you can increase the degrees of the angle of your pitch depending on your usage. So if you want to use the controllable pitch propeller, so there are hydraulic oil that must be used in order to rotate these blades of your propeller. Okay, so the proper viscosity must also be used in using this hydraulic oil. Okay, next we have hydraulic systems on board. So the viscosity of hydraulic fluids must be properly used. Proper viscosity must be used in order to have a proper smooth operation for our hydraulic components. So first we have the steering wheel for the ship. This one, steering wheel. We also have this one. This is a thruster for the ship using hydraulic. We also have hatch covers that will be opened or will be activated using hydraulic pressure. So using the proper viscosity for our hydraulic system will provide smooth operation of our hydraulic components. Okay, fuel systems. So the fuel systems greatly depend on the proper viscosity of the fuel. So if the viscosity of the fuel is in its right reading, like for example, most of the ships have 15 centistoke of fuel viscosity on the system. So if you will follow the manufacturer's manual depending on its recommendation, so the better the fuel viscosity, the lower the viscosity, the better the atomization of fuel, the penetration of fuel, and the combustion of fuel will be more efficient, and the engine performance will be on its optimum performance. Okay, so viscosity in fuel is very important also. Okay, we also have cargo pumping system. Well, it also uses hydraulic system. So these pumps will operate using hydraulic, and viscosity is very important in these types of systems also. We have cooling systems on board, especially if you're using coolant. So proper viscosity of coolant is very important for proper operation of cooling systems. Okay, that's it. So let's determine the viscosity of liquid according to its type and its applied temperature. So on ships, so if you want to determine the viscosity of a liquid according to its type and its applied temperature, you can use some tables in the manufacturing manual. Like for example, here we have here a table. So we have here a table for, we have here, this line will be the marine diesel oil, this will be the marine gas oil, this will be the bunker fuel, bunker fuel 30, so viscosity 30. This one is IFO 60, IFO 100, IFO 180, and HFO 380, and different types of fuel. Okay, so for example, if you want to, for example, let's try the fuel system. So this will be used for the fuel system. Okay, so as you can see, the recommended viscosity for our fuel is around 13 to 17. Okay, so that is the recommended viscosity of our fuel. So if ever you will be using IFO 180, for example, so here is the line for IFO 180. So if you want to use, for example, let's try 15 centistoke. So if, or maybe 13, let's try the minimum. So 13 centistoke. So if you want to maintain a 13 centistoke of viscosity to a IFO 180, you should have a temperature of, let's look down here below. So let's look this one. Okay, this one. So what temperature below is connected to this IFO 180 at 13 centistoke? So it's around 125 degrees Celsius. So that's estimatedly around 30 degrees Celsius or less. So 128, let's say it's 128. So at 128, you should maintain the fuel temperature of your IFO 180 at 128 degrees Celsius to maintain a 13 centistoke of viscosity. So using this table, we can we will know how what temperature we will use, or what viscosity, or what kind of fuel does this what is the recommended temperature and viscosity for different kinds of fuel depending on your usage on board. So that's how we determine the viscosity of a liquid according to its type and its applied temperature. Okay, so there are tables on board, so you should read the manual occasionally so that you will be more familiar with the different specs or specifications that you need. Okay, next, describe between viscosity and flow at low velocities of a liquid. So there are different ways why the viscosity or the velocity of the liquid flows at low velocities. So first, we have very used oil. So as the oil is used, so there will be more impurities that will be mixed into the into the oil. So the viscosity will be greatly increased, and the velocity will greatly decrease. So there are different if a liquid has high viscosity, it will flow more sluggishly at low velocities because it offers greater resistance of flow. Conversely, a liquid with low viscosity will flow more readily at low velocities because it offers less resistance. Okay, so what are the systems on board in which we use low velocities? Okay, first, for cooling water system, so it is very important to have low velocities for cooling water system so that your cooling water will stay longer into the system, thereby increasing its heat transfer or its heat absorbing capacity. So it will increase since you have a low velocity of cooling water. So if your cooling water will move fast into the system, so it will barely absorb any heat from the engines. But if you slow down the velocity, if you lower down the velocity of your cooling water system, then the longer it will be moving, the longer it will stay in the system or in the engine, the better it will be absorbing heat from the engine, thereby cooling down the engine or preventing overheating. Okay, next. We have fuel oil transfer system. So it's very important to have a low velocity fuel oil transfer system to prevent oil spill, because if you will increase the speed of how you transfer fuel from tanks, so the faster the speed of the transfer, so the higher the risk of overspilling of fuel oil. That's why in bunkering, during bunkering, when the tank is almost full, we slow down the velocity or the flow of the bunkering or the flow of fuel into the tanks to prevent oil spill. So it is very important for safety purposes. Next, for bilge water system, so it is very important to have low velocity for bilge water system because in bilge water system has oil and water combination in tank. So it is absorbed from the bilge well. So from the bilge well, all the oil and water mixture will be absorbed or will be sucked in by a bilge pump and put it into a bilge water tank. And from the bilge water tank, depending on the right location, the right timing, and if it's already okay to use the oily water separator. So if you're in the right place and the ship is moving at the right pace, at the right speed, and you're in the correct place, far away from the sea, so you can use the oily water separator. So the oily water separator will be the one that will suck the water from the bilge water tank and then separate the oil and water and then discharge clean water overboard. So you can discharge water or oil overboard not more than 15 ppm, so less than 15 ppm. So if you have a bilge water system that has low velocity, so you can properly monitor 15 ppm or less than 15 ppm of clean water, and then you can discharge it overboard. But if you have a high speed or high velocity oily water separator system, so there will be a higher risk of oil spill overboard. So to prevent that, we should have a low velocity of oily water separator operation. So if ever the ppm increases up to 15 ppm, so automatically the water will be recirculated back into the ship, into the bilge water tanks. Okay. Next, potable water system. So what is this? These are the drinking water usually. Okay, so how does this work? So from the freshwater tank, so it will enter into valves or it will be sucked. So we have freshwater tank in which we store our fresh water. We have non-return valves to prevent returning of any liquid back to the tank. We have pumps and we have hydrophore tank. So the hydrophore tank is full of, if it's empty, it's full of air. And then when the pump start, the fresh water will be sucked in by the pump, and then water will go into the hydrophore tank, filling up the hydrophore tank, while the air at the top will be compressed. And then when it compresses, so the buildup of pressure in air pressure increases. So at different setting, for example, the setting will be 7 bar. So if it reaches 7 bar, it will automatically send a signal to the pump to stop. So the pressure inside the hydrophore tank is already 7 bar. And then if ever you will use a water in your cabin, if you want to drink water, if you want to wash dishes, use laundry, or take a bath, then the pressure of the air, 7 bar, will be the one pushing the water into your cabin, into different parts of the ship, into the bridge, and everywhere that uses water. And then if the pressure goes down, since water is going up into the ship, all over the ship, then air pressure will, the space inside the hydrophore will increase, thereby the air pressure will be decreasing. So let's say it will move to 4 bars. So for example, the 4 bar is the setting for the pump to start. So at 4 bars, the pump will send signal, the pressure is, we will send signal, pressure transmitter will send signal to the pump to start, and then increasing it to 7 bars, and then the pump will stop, and then it will start again if the pressure inside the hydrophore tank will go down to 4 bars. So let's say that's the setting. Okay, so that's how it works. And then for low velocity, so we don't really need high velocities for our potable water, so that we can also control the water. We prevent spill when using it, and so that's why we also need low velocities of flow or water flow in our potable water systems. Okay, next we have hydraulic system. So we don't need high velocity for hydraulic system. We only need high pressure for our hydraulic systems, not high velocities, also low velocities. Okay, next we have to solve illustrative problem to determine velocities of a liquid in terms of its viscosity. So our formula will be volumetric flow rate Q is equals to pi r to the power of 4 divided by 8 times U, which is the viscosity of the fluid, times the difference in pressure. So as you can see, the given, the viscosity is already given at 0.05 Pascal second. And then the radius is 0.1 meter, and the pressure difference is 100 kilopascal along the length of the pipe. So determine the average velocity of the fluid using formula. So using the formula, we will have to put all the values into the formula, and then the answer will be flow rate will be 785.4 times 10 to the power of -6 cubic meter per second. And then to solve for the average velocity, which is the one we are looking for in the problem, so we will have to use our Q is equals to area times velocity. So cross multiply, we have to cross multiply velocity is equals to flow rate Q over A, and then put the formula. Q is 785.4 times 10 to the power of -6 cubic meter per second divided by the area, which is pi r squared, or pi times 0.1 meter squared. So the answer will be 25 meter per second. So to be sure, you can use your calculator. Maybe there will be a mistake in my computations. Okay. Next, explain the onset of turbulence in terms of disturbance of uniform flow due to high velocity. So this topic will be more on the Reynolds number. So this will be discussed on our next topic. Okay, next, cite onboard system operation that encountered onset of turbulence. So usually onboard ships, the one that encounters turbulence are the propeller, we have the stability control system, the bilge and ballast control systems, anti-roll stabilization systems, dynamic position systems, we have weather routing and navigation systems, hull and structural structural monitoring systems, cargo handling and stability systems. So those are mostly the systems that have turbulence on board. But to some, on our daily basis, or on daily works on for marine engineers, so you mostly in propellers we have turbulence, in stabilizers we have turbulence, of course, also in pipes. So in pipes, if there will be a bend in the pipe, so on the bendings of the pipes there will be turbulence in there. On valves, if the valve is not fully open or slightly open, so there will be turbulence in the flow of the liquid. What else? In pipings, if the piping is in have an increasing pipe from small to big pipe, or from big pipe to small pipe, so there will be losses, there will be turbulence that will occur, and then losses in the system. So in bending of pipes, what else? So there are different fittings. In some fittings, so there will be turbulence also in there. So there are different systems on board in which it usually encounters onset of turbulence. Okay, so that's it for this topic. So I hope you have learned so many things, and I hope I have shared some insights and some informations for you and for our marine engineering cadets and students. Okay, so I hope to see you on our next video, and God bless everyone.